In this lesson, I'm going to introduce the concept of a tangent and a secant. Now both tangents and secants are defined with respect to some function. Therefore, we're going to start by drawing on a graph and some function on it. So first we'll start with the definition of a secant. A secant is just a line drawn between 2 points on the graph of a function. Now before we go ahead and find the equation of a general secant, let me go ahead and do a specific example first. So suppose I defined a function f of x and gave you its graph. Suppose we wanted to find the secant through this graph that cuts the x-axis at x equals 1 and 3. Now to actually find the equation of this line, we're going to want to start by actually finding the coordinates of these points on the graph. We can do this by substituting their x values directly into the function to find the y coordinates. So I just fast forwarded this, but I started by subbing in 1 into the equation, so I replaced all the x's for 1's, and then when I put it into the calculator, I got the number 4. This means that the first point is at 1, 4. After this, I then replaced all the x's for 3's, and then when I subbed this into the calculator, I got the number 8. So this means that the second point is at the point 3, 8. Now that we have two coordinates, we have to remember that 2 points make a line, and therefore we can just treat this like we're finding the equation of a line between 2 points. To begin with, I'll go ahead and choose some general points on the line, x, y. Now I'll go ahead and label the points we were given, a and b, and the point that I chose can be called p. So I just want you to remember that in order to get the equation of a line, the gradient between a and p has to be the same as the gradient between a and b. Now things are looking a little bit cramped, so I'll just go ahead and move some pieces out of the way. Now to find the gradient for AP, I'll draw a triangle beneath a and p. Now the width of this triangle is just x minus 1, and the height of this triangle is just y minus 4. Therefore the gradient between AP is just the rise over the run, so it's just y minus 4 divided by x minus 1. Now to find the gradient between a and b, we should also draw a triangle between a and b as well. Now the width of this triangle is just 3 minus 1, so it's just equal to the number 2. And now the height of this triangle is just 8 minus 4, so it's just equal to 4. And now this tells us that the gradient between a and b is just 4 divided by 2, which is the same thing as the number 2. Now if we just go ahead and move the x minus 1 over to the other side, and then we move the negative 4 to the other side, we now have the equation of the secant between the points at x equals 1 and 3. Now that you can see how we do a specific case, let's do it in the most general case as well. Just like we had in the example, I'll go ahead and label the x values a and b. And we also know that the coordinates of the points a and b are a f of a and b f of b. To get the equation of this secant, we pick some random points on it with a coordinate x and y. So we want the equation of the secant. Just like we did in the example, we can say that the equation of the secant is given by equating the gradients between a and p with the gradient between a and b. Now we can find the gradient between a and p by drawing a triangle beneath a and p. Now the height of this triangle is just y minus f of a. And the width of this triangle is just x minus a. Now this just means that the gradient between a and p is just y minus f of a divided by x minus a. And now we can repeat the same process for a and b. Let's start with the triangle below a and b. Now this time the height is given by f of b minus f of a. And the width is just given by b minus a. And because the gradient is just the rise over the run, the gradient between a and b is just f of b minus f of a divided by b minus a. Now we can go ahead and actually rearrange this formula by multiplying both sides by x minus a, just like we did in the example. And then we can go ahead and move the f of a to the other side and swap it for a plus. And now this equation that we have is just the equation of a secant between a and b. So now that we've finished discussing what secants are, it's time to talk about what a tangent is as well. In order to properly understand a secant, I just want you to imagine that we had a car driving along the direction of the function. As you can clearly see, the car is not facing the same direction as the secant we drew. In fact, even if you were to actually move the point B, you can actually never draw a secant that goes in the exact same direction that the car would be facing at this moment. In a sense, this actually gives us a great definition for what a tangent should be. You can say that the car has the exact same gradient as our curve at this particular point A. Now this point that I've drawn on here is the tangent, and in a sense, it has the exact same slope as our curve at this particular point A. Now, unlike a secant, a tangent only needs a single point to be properly defined. If I was to bring back our car from before, I want you to imagine that we've taken a photo of the car at this specific time. In a sense, the tangent captures the direction that this car would be moving at this instant in time. Therefore, we call this the instantaneous direction of the car. Now, let me go ahead and give you a simple example where we can actually find the equation of a tangent. So for our example, I want you to imagine that I started with the exact same function that I showed you earlier. Okay, so if we wanted to find the tangent at this point 3,8, I want you to imagine that it's going to move roughly in this direction over here. So I'm going to start by actually drawing it on. Okay, so if this line over here is actually the tangent to this graph, the real difficulty associated with finding it is the fact that we don't actually know 2 points on this tangent. Now, in order to define a line, you can do so by finding 2 points, or you can find 1 point and get a gradient. Now, if the tangent's going to be defined purely by using the function, it's not really going to make sense to try to take 2 points on the function. So instead, we turn our attention to actually finding the gradient of this line somehow. Now, before we actually try to find the exact gradient of this tangent, the first thing I'm going to do is I'm going to try to approximate the gradient. So, as you know, to approximate gradients, we draw triangles under lines. So let me go ahead and draw the triangle for this gradient. Now, to actually find the gradient of this triangle, as we know, it doesn't matter how large the triangle is. So I've actually drawn a really large triangle to make it easier to read the values of. So finding the gradient just requires you to find the amount of rise and divide by the amount of run. It looks like we're rising from 8 to about 23, so the rise is about 15. But the run is exactly 3 in this case. So therefore, to get the gradient of the tangent, you just divide 15 by 3 and you'll get 5 as an approximate answer. Now of course, this picture over here is a hand-drawn picture, and that means this triangle over here isn't going to be completely accurate. So this height of 15 and this run of 3 is not going to be perfect. Now, because this triangle is not perfect, the gradient we found by using it is of course not going to be perfect either. It is just an approximation. Now, despite the fact that this picture isn't perfect, we could make it more accurate by drawing a larger triangle and making this diagram a little bit more to scale. But the real difficulty lies in actually drawing this line perfectly, and that's going to be really tricky in general. Now, since we've determined that the gradient is approximately equal to 5, if we choose some random point on the line, then the gradient between these 2 points needs to be 5. So that's just going to be y minus 8 divided by x minus 3. So if we just pick any point on the line, this is going to be the equation that it must satisfy if it's on the tangent. So we could just rearrange this formula to make y the subject. Okay, so using this approximation to the gradient, we came up with an approximate tangent. But you might be wondering, how do we actually get the exact gradient? I mean, these approximations surely aren't it, are they? And you'd be right for thinking that. Our initial studies of calculus are actually going to help us find the exact equation of this tangent. That's actually going to be the first problem that calculus tries to solve. Now, if you didn't really care what the exact tangent was, you could roughly do this and things would be okay. But it is a bit of a long process, and it turns out that calculus is going to give us a shortcut that's actually going to give us the exact answer. Okay, and that's really all, so let's just summarize everything we talked about. We said that a secant is just a line that's drawn between any 2 points on a particular function. We then turned our attention to actually finding the equations of these secants, and we found that they always obey this equation over here. After finishing our discussion on secants, we then talked about tangents, and we said that tangents are very much like secants, they're lines connecting functions, but they actually have the exact same gradient as the function at a particular point. We said that it was going to be pretty hard to actually find the equations of one of these tangents because they only go through 1 point. And we know that in order to define a line, you either need 2 points or you need a point and a gradient. Since we can only really rely on the 1 point that we have, it turns out that we're going to need some kind of clever way to find the gradients. And this is actually going to be the first stop for calculus. Using calculus, we're going to be able to find the gradients to tangents in general, and then once we know that, we can find their equations very easily. Okay, so now that you've actually seen how tangents and secants work, maybe it is actually time that we started looking at how to find their gradients. So we're going to do that in a future lesson. So without any further ado, we've completed our discussion on tangents and secants.